Hey, everyone. Welcome to lecture two. This lecture is going to be about vectors. So we still haven't gotten to physics yet, but these are very, very necessary in order to do good physics. And they also tend to be some of the hardest concepts to grasp. So even though it's not really physical concepts, when I was doing labs at a different school every semester, every quarter. This would be the hardest lab for people to finish and to get done. So, uh, just I think I in the homework gave a pretty good variety of questions. So just make sure that you're able to do all of those. And then next week in the labs, we're going to have another vector lab, which is going to be based off of this instead of just doing Excel for another week. So basically, what we need to define when we're defining vectors is we need to talk about the difference between it and a scalar. So a scalar is a quantity that has some magnitude but no direction. So for example, time and speed are scalars because they give you some information about a quantity and they do have units, but they're not going to tell you what direction the quantity is going in because all it tells you is if you're going 60 miles per hour on the highway, it doesn't tell you if you're going northeast, south, on the 210 north or south or anything like that. All it tells you is your instantaneous speed. So in order to do that, you need to have a vector, which is a quantity that has both magnitude and direction. So we have speed that I was talking about, and that is a scalar. Select. This is being a little difficult right now. There we go. So speed is a scalar because all it does is tell you the speed at a given time. But if you're talking about going uh in a specific direction at a certain speed, so if you are talking about going north or south on the highway, uh in a different speed, then what that is called is velocity. And then another vector that we're going to be talking about this lecture is going to be displacement, which is a very easy way to think about vectors because all that displacement is the vector between a starting position and an ending position. So vectors are drawn from tail of an arrow to the head of an arrow. So from here, from the A to the B, would be a vector for displacement. And what the path might look like, what you might be going through when you're going from A to B might look like this, but the overall displacement is just going to be this vector pointing from the original position to the final position. And then another thing to note about vectors, uh, drawn as an arrow from head to tail, or from tail to head. Uh, Magnitude is proportional to the length of the so if we're talking about say is proportional to the length of an arrow. So if we're talking about say uh oh, never mind. If we're talking about two vectors A and B, which are both force vectors, that's a kind of janky arrow for B, but you get my point. So if we're talking about two vectors A and B, which are both force vectors, then the longer one is going to have more force acting on the object than the shorter one does, because magnitude is proportional to the length of the arrow generally. And or generally it's good practice to write it like that. So when I'm just if we don't know the magnitude immediately, then we can just draw some arrows and uh use that as our vectors. But if we do know the magnitude, then it is good practice to draw them proportional to the length of the arrow. Let's see what else about basic uh vectors. So the way that they're also drawn out is as whatever variable you call the vector with an arrow on top of it, or you can have something called a unit vector, which has a hat on top of it instead of an arrow. So uh, unit vectors have arrows, unit vectors have hats. And what a unit vector is a vector that has a length of 1. So what basically the unit vector is telling you is that you have a vector, which is a quantity that has both magnitude and direction, and then the unit vector just tells you the direction. So uh, if you have some quantity A in the unit vector direction, then the unit vector direction can be pointing in, say, the x-axis or the y-axis or whatever, and the magnitude of the vector is going to be the magnitude of A in the unit vector direction. So that's why we use unit vectors. And then the most commonly used unit vectors are going to be are for the uh, axes x, y, and z, or if you're talking about polar coordinates, uh, then it would be R and T, where R is the distance from your origin, and T is the distance, is the direction perpendicular to the unit, uh, to the R unit vector, which is going to look like, so for XYZ, then you just have I, J, and K in the X, Y, and Z directions, which is just like your normal Cartesian coordinate system, which looks like J, like this. So just how you draw out a normal 3D Cartesian graph. If you've ever done that, if you haven't, I would be really, really surprised. But I, J, and K, X is I, J is Y, and Z is K. And for polar coordinates, what you're looking at instead is a disk where you start out at the origin of the disk, like you start out at the origin of Cartesian coordinates, and you go to some point R, which is some angle off of the x-axis, and then R is just going to point along the vector, right? So it's going to point from the origin to the tip of the vector, and then T is going to be uh, perpendicular to that, going in the direction of increasing angle. So that's what polar coordinates are. Uh, Another example is you just have a disk. Uh, you go out some length along the disk, and then that vector is going to be pointing in the r hat direction, even though it's not pointing anywhere in the x, y, and z axis. It is pointing directly along the r hat axis, because the definition of the r hat axis is just from your initial origin point to the final point that you're looking at. And then it's going to have some angle, which we're going to call the Greek letter phi, which is what it makes with the x-axis. Okay, so that's the basics of uh one-dimensional vectors. Uh One thing to note is that if two vectors A and B are equal, in magnitudes and pointing in the same direction, meaning they are parallel, then that means that A is equal to B. So in this case, even though they have different origins, and they are in different positions, since they're both parallel and they both have the same magnitude, A is going to be equal to B. Uh, if A and B uh, are anti-parallel and pointing in opposite directions, then A is equal to negative B. So in this case, it would look something like A and then B, anti-parallel pointing in opposite directions. So A equals negative B. Uh, and then just another couple of properties of vectors is that uh yeah, vectors can be perpendicular, no, obviously. They are vectors are commutative, associative, have the additive identity, and can be added and subtracted. So what I mean by commutative is that A plus B equals B plus A. Associative is the same property that you see in just number additions, where A plus B plus C equals uh oh no uh A plus B plus C. Then when you add A plus 0, so a vector that has no magnitude or direction, then that is just going to be equal to A, and they can be added and subtracted, where I'll show you how to add later, but A minus B is equal to A plus negative B. And then the last thing that I can think of, I feel like there's something that's slipping my mind right now, but it isn't in my lecture notes. So the last thing I can think of is that uh, actually, I'll get to that in a little bit after I define a little bit of how you write out these questions. So, uh, the way that you write out vectors is that let's talk about it in two dimensions. It's going to be AX, AY, where this is magnitude pointing in the x direction, and this is the magnitude pointing in the y direction. So if you are going 45 degrees off the x-axis and pushing with a magnitude of 2 newtons of box 45 degrees off the x-axis, then what that's going to get you is that you're going to have a magnitude in y, a magnitude that's pointing in the y direction, and a magnitude that's pointing in the x direction. And what those magnitudes are going to end up being is the square root of 2 newtons in both directions. So this is also can also be written as AXI plus AYJ. And then if we introduce a third dimension, then it's going to be AZK, where these are again just the unit vectors in the x, y, and z directions. Okay, so if these are the unit vectors in the x, y, and z directions, then you see that AX is just the magnitude of the vector pointing in the x direction, AY is the magnitude pointing in the y direction, AZ is the magnitude pointing in the z direction. So if we uh, draw this out, then the distance from here, from point A, no, not A vector, that was just silly. Not B vector either. So from point A to point B is the displacement, is going to be the same as you going along the x-axis some distance AX, and then going up the y-axis some distance AY. So that's what it means by the components AX, AY, and AZ. So where we're doing a two-dimensional Cartesian coordinates. And then if they have some angle phi, then that's going to be how you're going to be able to convert from polar coordinates to Cartesian coordinates, which are x, y, z, and vice versa. And then another thing to note is the commutative identity, or the social divide. No, it's commutative, I believe, where if you go up AY first, and then go to the side AX after that, then that's still going to get you from A to B. So AX plus AY equals AY plus AX. Okay, so this is kind of getting a little crowded, but hopefully if you've been paying attention, you should still be able to parse this. Um, and then from here, the way that you get the X, Y, and Z components, we're just not going to worry about Z components right now. We're going to let this go to 0 and assume that's just X and Y in the polar plane in the XY plane and ignore Z components because I'm pretty sure that even when they talk about three-dimensional analysis, they don't uh say what yeah, they don't say what uh how you get Z component as well as the X and Y components other than just finding the angle between uh two vectors instead of finding the angle between all three, the polar angle and the azimuthal angle if you've done that sort of geometry before. But what I'm saying is don't worry about it, honestly. Uh, uh, we'll have to worry about it, then I can bring it up on Monday. But you have this vector A, which is made up of the components AX and AY. And it has the angle phi. So AX is going to be the adjacent angle or the adjacent side, which is going to be the hypotenuse times cosine of phi, because cosine of phi is adjacent over hypotenuse. And then the hypotenuse is just going to be the magnitude of A, which is given by this notation, just A with two lines to either side, times cosine phi, and then AY equals opposite equals hypotenuse times sine of phi, which is where sine of phi is opposite over hypotenuse, equals A sine phi. So this is how you get X and Y components from the polar coordinates, from this angle and this magnitude of in the direction of the vector. So how you get polar coordinates from, oh, so how you get polar coordinates from X and Y components is using the Pythagorean theorem, so that A is equal to the hypotenuse, which is equal to the square root of opposite squared plus adjacent squared. Because remember, any right triangle, like this is going to be, because AX and AY are perpendicular to each other, the two sides of the triangle are equal to uh, the two sides of the triangle squared are equal to the hypotenuse squared. So this is going to be equal to square root of AX squared plus AY squared. And then tangent so we have ax and ay, and we know that sine of theta or sine of phi and cosine of phi are proportional to ay and ax. So a sine phi over a cosine phi equals tangent of phi equals ay over ax. So phi can be found by taking the arctangent of ay over ax. Okay. So yeah, that's how you convert between x and y magnitudes, and that's how you find the x and y coordinates and polar coordinates. Uh, and then one last thing when talking about two-dimensional analysis is that uh, some number c times a is going to be distributed through the vector is going to be equal to c times axi plus ayj plus azk, which is going to be c axi plus c ayj plus c azk. So for example, if we have some vector just pointing in this direction, a, and then b equals c times a, then or if c b equals 2 times a, then it's going to be the same vector but twice as long. So if c equals 2, which means that both the x and the y components are going to be twice as long as they were for A. So this is just what it looks like when you multiply a vector by 2, it just gets twice as long, which means that this is AX, and then this is BX, which is equal to 2AX. And then this is AY, and then this is 2AY. So like you see, as you can see kind of graphically here, it's not a great proof, but just looking at it, you can see that, uh, yeah, you can see that uh, B is going to be twice as long, which means that the components BX and BY are going to be twice as long as AX and AY. So hopefully that should be something that you can just see here. Uh, so as kind of our final note for two-dimensional Vectors, we are going to talk about adding and subtracting. So if you have the a vector a and a vector b, then a plus b can be graphically done by going along from the tip or from the tail to the tip of A, and then from the tail to the tip of B, because you're just going to be going um, as far along as you did in the AX direction, and then you're going to be going that extra distance along in the BX direction. And the same thing is going on with AY and BY. So because you're just going along some distance in the X direction and some distance in the Y direction, then put when you put the tail of the B at the tip of the A, then that's just going to take you some distance further out in the X direction and some distance further out in the Y direction that you would be going if you took A plus B and did it numerically. Because you have your A component, AX component, you have your BX component, you have your AY component, you have your BY component. You just add those to each other and get the total resultant vector, which is going to be in green. Okay, so hopefully that makes sense. That's just how we graphically do it. A minus B is equal to A plus negative B. So that is going to be the same sort of thing. It's just starting out, you have your A vector, but instead of going along in the same direction as the B vector again, where this is the B vector, you instead go in the opposite direction of the V vector. Uh, and then that's going to be A minus B. So that has a resultant vector that basically just looks like it's completely along the x-axis. And then you can also do more complex analysis with this. I think it's probably going to be, I think there's a problem in your homework that goes over this, but graphically, but you can have A plus B, you can have A minus B, you can have A plus 2C plus 3, uh, and you can plus 3B minus 4D, and all of these different things that you can do just by doing this uh, tip to tail or tail to tip method. And keeping your variables the same thing. But what You just need to keep in mind when you're doing that is that you just go tail to tip for all of the different vectors that you're talking about. So A plus B plus C, A, B, and then back a little for C, is going to be something that you can just draw out. Yeah, it's just something you can draw out if you just draw tip to tail or tail to tip or tail to head, whatever you want to call it, and uh just follow the vectors, go along one vector, then the other vector, then the other vector, and then if you need to go in the opposite direction, you can do that. If you need to multiply, you can just make them longer or shorter as the need may be. And that's basically all I have to say about the graphical method for adding vectors. But I do think that this is probably going to come up on the lab coming up. So there we go. Let's see. Let's do, I'm trying to find an example problem for just adding different vectors. So let's say that A equals 2, 3, B equals 1, 0, C equals 2, -1, where again, this is AX, this is AY, and so on and so forth. Then in order to find A plus B, we take equals 2, 3 plus 1, 0 equals 2I plus 3J plus 1I plus 0J is equal to 3I plus 3J is equal to 3, 3. So just make it so that break it down into I and J components, add them together, and then just these are the same sort of things. I just broke it down explicitly into I and J components, and then since I and J are perpendicular to each other, they can't yeah, you can't add them together. So 3 is just in the I direction plus 3 in the J direction equals 3 comma 3 in parentheses. So 2, second problem with the same sort of thing is going to be A minus 2C. And I think this is actually all that's really necessary to do equals 2, 3 minus 2 times 2 -1, which is going to be equal to 2, 3 minus plus -2 times 2, comma, -1 times -2. Because I'm just distributing this uh this -2 here into the x and y components of C. So this is going to be equal to 2i plus 3j minus 4i plus 2j is equal to -2i plus 5j equals -2, 5. And yep, that uh is basically all you need to do. Just treat the i's and the j's, the unit vectors, like their own variables and don't mix between them, and you should be fine. So with that said, we are going to go to vector products now, which is, you know how to add vectors now. You can do that with 2 or 3 dimensions. All that changes with 3 dimensions is that you have the k unit vector now. And now we're going to learn the 2 ways that you multiply vectors together. The first is the scalar product, which is also called the dot product, which is just defined as A dot B is equal to A B cosine phi, where phi actually, just a second, yeah, it is phi. Where phi is defined as the angle between A and B. So you have A, you have B, and phi is the angle in between them. So uh, the way that, I'm not going to really derive how they came up with this, but what this actually means is that A dot B equals AX BX plus AY BY plus AZ BZ, which is, as you know, not going to be a vector. It's just going to be a scalar, which is why it's called the scalar product or the dot product. And uh, a way that you can see that's going to be the angle between these is if we just decide that B is pointing in the x direction, phi, and then A is pointing some phi direction off of that, then A is going to be A cosine phi, which is AX, B cosine 0, which is BX, plus AY times 0 plus AZ times 0 because by and bz are both equal to 0 because we defined b to be entirely in the x direction. So cosine of 0 is 1. So this ends up being a, b, cosine phi. So that's just the proof that a dot b equals ab cosine phi if we take this definition first, axy bx plus ay by plus az bz. And then that can also, what this also tells you is that it can be a measurement of how much they overlap because cosine phi starts out at 1 if they're completely in the same, if the two vectors are if the two vectors are completely in the same direction, then cosine phi will be 1. And if they're cosine phi will just get smaller and smaller the farther apart they are until they hit perpendicular, in which time cosine phi is going to be equal to 0 when phi equals 90 degrees or pi over 2. So what this also tells us is how much they overlap. So you have A, B, and A cosine A cosine phi is going to be the shadow of A along B. So it's going to be how much A drops down and fills fulfilled fills aligned with B. And then that's also going to be the same thing as we take so AB cosine phi is going to be this value, A cosine phi, times this value, B. So it's just going to be how much A overlaps with B times the magnitude of B. And then if we do it the other way where A is on the x-axis, then it's still going to be how much does B drop down and how much do these two overlap? So it is a measurement of how parallel they are. So the final thing basically that we're going to go over is the cross product, which is really really difficult. I probably shouldn't have said that it was really difficult. That's just demoralizing, but it's really difficult to get your head around when you're first learning it. And all this stuff is kind of stuff that you're going to learn in math in like 2 or 3 semesters. So you're just learning it here first, and then you're going to get a deeper understanding of it in math, where they'll spend like a month going over these concepts instead of just one lecture. Uh, let's see. So the vector cross product, if the vector product, otherwise called the cross product is defined as A cross B uh, equals C, where A cross some. Okay, I'm going to try to make it obvious that A and B are not perpendicular to each other. A, B, and then C. When you take in an input of two vectors, A and B, then they give you out a third vector which is perpendicular to both vectors, C. So if A and B are in the XY plane, it doesn't matter if they're pointing in the X direction or the Y direction or just any direction like that, then A cross B is going to be pointing in the Z direction. So uh, the way that they define this in the book is that A cross B is some vector C, and then the magnitude of C is the magnitude of A, B, sine the angle between them. So if uh, the dot product is a measurement of how well these two vectors align, the cross product is a measurement of how perpendicular they are to each other. So C equals AB sine theta or sine phi. And then if that's the case, then A cross B equals negative B cross A. Because AB sine phi, if the phi is going in the opposite direction, negative phi, then sine of phi goes to negative sine of phi because uh, the sine function is an odd function, which means that sine of negative phi is equal to negative sine of phi instead of being an even function where sine of cosine of phi, negative phi is equal to cosine of phi. So if phi goes to negative phi, then sine of phi goes to negative sine of phi, which means that you have your two vectors A cross B. If you go in the opposite direction and go B cross A and define B to be going in the opposite direction, or B to be A and A to be B, then C would be pointing down in the z-axis instead of up in the z-axis. So yeah, this is the bones of what a cross product is, but how you actually use it is that you realize that I cross J is equal to K, J cross I, or J cross K is equal to I, and K cross I is equal to j. So basically what I was saying, if the vectors are in the xy axis, then it's defined that the resultant product will be in the z axis. If uh in the positive or negative z axis, and we define it to be the positive axis uh by something called the right hand rule, which I can show you. It's kind of hard to explain over video, so if you have any questions, ask me in class, and I'll just go by person to show you how to do it. But basically, you define it so that your right, if your two forefingers, use your right hand, your two forefingers are pointing in the direction of A. Your two lower fingers are pointing in the direction of B, then whatever direction your uh, thumb is pointing in is going to be the direction that C is going to be pointing at. So you use your right hand, and then you point in the x-axis. Y-axis is, in my case, going into the screen. Then the resultant vector will be going off in the z-axis. If you point in the y-axis for your A, and then point up in the z-axis for your B, then C will be pointing in the x-axis. And if you point up in the z-axis for A, and to the side in the x-axis for B, then your resultant vector C will be pointing into the y-axis. So basically, that's just how we define these things. It has to be perpendicular to both vectors. So in this case, uh, we define it so that it goes from A to, or K to I to J, as you go from I cross J to J cross K to K cross I. And then it's just the unit vectors, because both units vectors, I and J, or J and K, or K and I, are going to have a magnitude of 1 because they're defined as unit vectors, and they're perpendicular to each other, which means that they're sine of 90 degrees, which means that that's also going to be 1. So it's 1 times 1 times 1 equals C, and then it's pointing just in the K direction, and the I direction, and the J direction. So by doing this, you can come up with a numerical formula. Oh, whoops. You can come up with a numerical formula for AXI plus BXJ plus C. Oh, that was very dumb. Sorry. AXI plus AYJ plus AZK cross uh BXI plus A BYJ plus AZ plus BZK, which is equal to AXI cross BXI plus AXI cross BYJ plus AXI cross BZK zk, which is just distributing through this AXI to all three components of the B vector. And then you do that for all three components, AY, AZ, and then just you're going to end up with, I think, 9 terms, 3 of which are going to cancel out, and the remaining of which are going to give you the formula for what is the cross product. Just a second, I'm trying to pull this up in another tab and it is not being very helpful. Okay. Uh, okay, so it wouldn't allow me to pull this up. What I'm pretty sure it's AYBZ minus BYAZI plus a ZBX minus BXA minus BX or BZAXJ plus AXBY minus BXAY K. So I wasn't able to pull this up. So this is just me doing the work in my math. So I would definitely uh check this against the book. So that is the main thing that it teaches you in the book. I'm also going to uh go for another way that you can do this. Nah, I think you're fine with that. I think we're fine for the day. Uh, there is another way to do this, but I think at the level that you are now, I don't want to overwhelm you with the matrix version of this. So I'm just going to leave you with this equation, which you should definitely check against the book to make sure that it's fine. And then that's basically all I have to say today. If you have any questions on homework or anything, go to the discussion boards or reach out to me personally. Uh, it looks, I haven't been able to get into the homework still. So it looks like the first two homeworks might just be due on paper as I try to figure that out. But they're going to be due at the start of class on Monday, no matter what. All right. Well, have a good day. I hope you learned something useful. Uh, and then stop recording.